So, hello all. Welcome to the Photonics chapter IIT Bombay. So, we are the Photonics chapter IIT Bombay, the branch of student chapter of Optical Society of America, as well as IEEE Photonics Society. So, we started this time our new platform called LAMP, Light Application in Modern Phase, and we started this platform from the International Day of Light, and we had lots of lectures series in this lamp series. So here are the some our previous talks, and now we started the symposium for from the August to October. It will go where we will discuss lots of softwares called Synopsys, Wraith, ANSYS Numerical, and then some characterization tools like Horiba and Oxfords. So we are started from the Synopsis, and last talk was by Mr. Praveen Joshi, who is the director of Fiber Optic Service Mumbai, and it was a wonderful talk. Today, in the continuation of that talk, Mr. Tung Yu Su is with us, and he's a senior application engineer in Synopsis, Netherlands, Europe. So today he is delivering talk on PIC suite and opto compiler. So Mr. Tung Yu, now stage is yours. So you can share your screen and start the talk.
Yeah, thank you for your introduction, and it's my great honor to have a talk here. So I would like to share. So in the section today we have three topics. The first topic is about the Synopsys Photonic Design Suite, and the second topic is about the opto compiler. The final topic is about the integration between Synopsys Centaurus Tcat and our self-device tool. So I'm gonna share my screen for the first presentation. All right. So let's check the first one.
Okay, so hi, good day. Welcome to join Synopsys webinar. And this webinar is Synopsys PIC design suite, and we are going to show you how to design your PIC chips from your idea to fabrication. My name is Tung Yu Su, and it's my pleasure to deliver this
Hello.
presentation to you guys here.
Hello.
So the first one is the first.
Oh yes, hello.
Okay. I think you shared your screen. It's not visible to me. Kishore is visible.
It's visible, Anush. It's visible.
Okay.
Yeah, continue.
Yeah, thank you.
The purpose of this webinar is to provide the latest design flow of PIC by Synopsys Photonic solution. And Synopsys Photonic solution focuses on a complete design flow for PDA. And this flow is based on the existing EDA flow. So we're gonna to do that. By the aid of this flow, we were able to move PICs from the research to mass production. And so what's the main issue between photonic and electronic circuit? So we will know that the challenge of photonics IC design is the routing shape, or we call curvilinear properties of waveguide. And these properties normally is not supported by traditional IC tools. Therefore, in order to provide a complete design flow, we need some functions described here. So based on this request, now we are going to show you the Synopsys design flow. So this figure shows our design flow. So we can focus on the first part, starting from option circuit for circuit level simulation and connected with Opto Designer with a bidirectional interface. And when the integrated circuit become more and more complicated, Code simulation with HSpice provides a powerful ability to consider the interaction between EIC and PIC. Moreover, layout versus schematic is always necessary when the circuit are getting more and more components. IC validators in this flow works perfectly with Opsin circuit and Auto Designer. Another part is if designers are not able to find suitable components in Foundry PDKs, this flow also supports our users to put their own component PDKs. That is what we say custom PDK in this flow, and the custom PDK can be connected with Opsin circuit and Auto Designer directly. And then in the final stage, when finished our layout designs, we can use Auto Designer to check DRC and export GDS to Fabrication. So that is Synopsys' latest flow, and let's start on each flow with demonstrations to figure out how it works. The first step here is from circuit simulation. When Photonic PDK in Opsin circuit, users are able to simulate the performance of PICs in a schematic point of view and analyze the parameters in the circuit. Of course, we support most of Foundry PDKs in Opsin circuit. So when the analyze was done, circuit model in Opsin circuit can be directly imported to Auto Designer for layout. And this interface is bidirectional. So that is when you finish the layout design in Auto Designer, you can import back to Opsin circuit to check the change of performance. So in Opsin circuit, both frequency and time domain simulation can be simulated, and most of commercial PDK are supported in Opsin circuit. Besides, the circuit model are able to connect it with Opsin because the most of our PICs are going to be deployed in system, and it also makes sense to design or optimize PICs from the system performance perspective. The other thing is the importance of this interface between Opsin circuit and Auto Designer is why we want to automate circuit to layout. And this flow enables users to refine and optimize the layout based on simulation result. So the main challenge here for this interface, once again, is we want to automate the whole process. So in the following demonstrations, I'm going to show you how to integrate Auto Designer and Opsin circuit and how to exchange the model with the same file. So let's see it. Okay, so we are going to use a demonstration to show you how to move our circuit model to a layout model. So in this case, we are going to use a complex band switch for our examples. And in these demonstrations, I'm going to show you some 3 features in this case. The first one is the layout generation from Opsin circuit to Auto Designer. So that will help you to move your circuit model from a schematic level to a layout level. And the second thing is auto routing features in Auto Designer. So in the case, I'm not going to define the connection in Opsin circuit. I'm going to use auto routing features in Auto Designer. The third one is schematic simulations because I want to do the auto routing in Auto Designer, and I want to put this model back to Opsin circuit to check the performance with and without auto routing to see what's the difference between them. And this features is very important if you are dealing with some coherent system, which is very sensitive to the phase change. So if you add actual routing between different components, they will introduce actual phase delayed for different paths that is for the waveguide. So that is a feature I'm going to show you. So now this is Opsin circuit, and I want to build a circuit model. So today I use 6 demo fab tunable filters. I choose them directly from a library here. So here I choose 6 demo fab tunable filters, and I build 4 input ports and 4 output ports. So now I come up with an idea that how to design my circuit. So I connect different ports in Upstream circuit. So that is the way I realize my concept of my design. So I connect the ports to the input ports and output ports I just define in this circuit. And I don't know whether it works or not. So in this case, now I already connected these ports. I'm going to save this model as a pic.momo file. And I'm go to my testbed here. This is my previous testbed, so now I clean it. Now I only have a broadband light source and 2 spectral analyzer. So I'm going to put my PIC designs in this testbed. So I use the compound component models. I load the model that I just saved, which is a PIC model. So you can clearly see the port you just define in your PIC, and now it's showing in this compound model. So I'm launched a broadband source to the input port 1, and I use the spectrum analyzer to analyze the spectrum for the output port 2 and 3. And I run Go simulation to run the simulation. And because there are a lot of bidirectional ports in this circuit, so it takes a while to run the iteration. And when the simulation reach steady state, we will get a result. So now we can check the spectrum for the second port and the spectrum for the third port. So they are different. So that is the way we use upstream circuit to check our design, whether this is what we want or not. But remember, we didn't define any connection between these filters. For example, this one, I just connect these 2 ports together, but I didn't define how far are these 2 components or what kind of waveguide they are using. So in this case, the result we just show here, we can call it like ideal case. The connection between different components are ideal. There's no any actual phase delay between them. But however, we need to do that. We need to do the connection. So in this case, I'm going to push this model from upstream circuit to Opto Designer. So at first, I need to save this model, and this Momo file will be saved and will be passed to Opto Designer. So now I'm open Opto Designer. As you see here, the script is generated automatically. So the script is generated according to our circuit model in Option circuit. And I click update. It will update this code for me, and of course run the auto routing features because we didn't connect it yet. So now here, it's very clear here you can see the connection between different filters are connected by our auto routing features. So now if you can try to modify the code, for example, you can try to move these ring filters into a more small space, or you want to copy them to another die template, which is what we are going to show in our final demonstration. So assume you are very satisfied with the connection. You are able to save it again. So for example, I save this model as another Momo file. I use the AR, stands for auto routing. So I save this model because I want to compare the ideal case and with the PIC auto routing case. So I save them as a different name. So I go back to upstream circuit. I open the one I just feed auto routing. That looks like the same, but if you check the connection here, if you right click connection here, there's nothing, it's just the connection. But if you go to the auto routing features, so here you can check, there's an option for you is view route. So the waveguide, the actual waveguide element you just added by our auto routing features will be shown here. So this waveguide will introduce actual maybe lows or maybe phase delay in your system. So now we go back to our system and we create another compound component, but this time we load another model, which is our model with auto routing. So we connect with the same light source, but this time I'm going to compare the same output port. So I use two spectrum analyzer to these two models, and I run Go. But before I do that, I need to check whether I'm going to simulate the routing. So we have three different kind of feature. If you choose ideal, we will not simulate the actual route. But if you use the direct route or route plus crosstalk, we will simulate the effect for with considering the actual route. So here I use the route plus crosstalk. So you start to simulate it, the effect. As you see here, it will take a little bit longer time because there's some complicated iteration is calculating in the circuit model. But this is a very good way for users to analyze the effect of the actual route in your circuit model. Because for this case, for the previous one, this case is very ideal. In the real case, you are not able to connect the two components without adding any actual waveguide in between. So now we are showing that we are pushing the layout back to a schematic again and to try to see the performance. So now we finished. So we click this model. This model is the one with our ideal case, and this monitor shows something introduced by our actual routing here. So as you see here, the performance is not exactly not the same. So I copy the file to in the same windows, try to compare these two models. So in this case, the green line stands for the ideal case, and the blue line stands for the case with route between different components. So in this case, if the routing feature here is exactly what you want, you can save the layout. But if it's not what you want, you can go back to change your routing. Maybe you can calculate the phase between different components. After Designer, we provide some phase-aware connection between components. But now we have this interface is a bidirectional interface between Opsin circuit and Opto Designer. So in conclusions, in this demonstration, I demonstrate the interface from Opsin circuit to Opto Designer. So the script in Auto Designer will be generated automatically, and you can use our new feature, auto routing feature in Auto Designer to connect the different ports for different components. And in the end, you can go back to Opsin circuit with the same model, try to analyze the effect for with different connection between different ports. So that is the purpose for this demonstration. So now we know how to export the circuit model from Opsin circuit to Opto Designers. But even though we have the PDKs in Opsin circuit and Opto Designer, but you will need a custom design of photonics, for example, like WDM component, filter rings in your design. So just like the foundry coordinated said, today 70% of the design are full customer. So in this case, we do provide an interface between device level simulators to Opsin circuit and Auto Designer. So that is, users are able to use our self-device tools or Central Tcat to run device simulation, create their own custom PDK, and export the PDK directly to Opsin circuit and Opto designers. So in the case, also users are able to use more than 4 algorithms for PIC design, like full-wave, beamprop, moprop, and FEMSIM. On the other hand, by the integration with Central Tcat, users are able to simulate and design the very accurate active devices and put these devices into custom PDK and make it exported to Opsin circuit and Opto designer. And how it works. So normally users are able to mix their own designs with Foundry PDK, but in order to do that, they need to know the Foundry technology information first. So starting for the Foundry technology information, like the width of the waveguide, the height of the waveguide, or the material, so we can create the geometry or the material in the RSLK layout. And we can use our simulators like full-wave beamprop to run the simulation, extract the X matrix, and the GDFS file as well. We combine them as the custom PDK. And the custom PDK can be imported into Opsin circuit for the S matrix part and export the GDS file to Opto Designer for the layout part. And the interface between Opsin circuit and Opto Designer is used the MOMO file that we just introduced for the previous demonstration. So by these flows, users can create their own PDKs and put it into Opsin circuit and Opto Designer. So just like if we want to make more complicated very large peak in the real case. So normally we use a mixture of the custom and foundry PDKs. So for example, custom components can be designed but just like particular foundries. So in this case, we design a ring in our subkit layout. We use full-wave to extract the X matrix, and we export it to Opsin circuit. So in this case, you are able to see your own elements in your workgroup dictionary and along with the Foundry PDKs. So now they are able to combine as the circuit and export to Opto Designer for the layout generation. Okay, so now we already know that we are able to use the custom PDK with the Foundry PDK together in Opsin circuit. So I'm going to show you some thing interesting in this demonstration. So in this demonstration, an I-ring resonator is going to use in Opsin circuit. And this I-ring resonator is a big ring combined with a small ring inside it. So there's some high order resonators in these cavities. So for this kind of case, normally it takes a lot of time and memories when you are going to simulate it only by numerical method like FTTD. So in this case, I'm going to divide this ring as 4 parts. The first part is the left-hand side is outer part coupler. And the middle part here, because of the symmetry, we have an inner part coupler, and these two are exactly the same. For the upper one and the downward one is exactly the same. So for the right-hand side here, I will use the same outer part coupler to combine this circuit. In order to do that, I will use the R sub K layout to generate the asymmetries for the 2 custom PDKs in a device point of view. And then I'll export the PDK to Opsin circuit and Opto Designer as well. So in Opsin circuit, I will connect these 4 components as an I-ring model, run simulation to check the resonance peak. We include the high order resonance peak, and then export this circuit from Opsin circuit to Opto Designer. So basically, there's a flow that we're gonna use today. So first we go to our circuit layout. So this is the part we define the geometry, we define the material in our circuit layout for this 3D case. And as I mentioned before, if we want to combine with the Foundry PDK like a demo fab PDK, I need to follow the technology information. So in this case, I define the width and height according to demo fab's specification to make sure I won't get any error like width mismatch in Opto Designer. So I design my components in our circuit layout, and then I export the S matrix for the different part. So the first part is the outer coupler part. I define the purple region here as the outer coupler part. I have port 1, 2, 3, and 4. So I calculate S matrix. I launch the field for port 1 and record the amplitude and phase for the 4 ports. And again, I launch the field for the port 2 and observe and record the amplitude and phase for all the ports here to make a S matrix. But in this case, I don't need to launch the field from port 3 and port 4 again because of the symmetry. These two data are exactly the same as we do that in port 1 and 2. So we just only simply duplicated the data to combine the S matrix. So this is the outer part here, and we're gonna see the inner part. So we define the inner part here with the same models, but in this case, we define a boundary here exactly match the outer part here because I don't want to introduce any extra waveguide connection between these two components. So I properly define the boundary. So once again, for opsin circuit and opto.
Hello. Hello.
Hello. Hello.
Yep, sorry. I think that I just get out the link. So let me do it again. Yep, so I already shared. Yep, sorry for that.
If you have parameters like the gap between a waveguide and or the radius or the actual delay line, you want to make it like variables, you're able to define that as a variable, and we have the parametric scan features for you to calculate the feature, a parameter in your PDK. So that is, you are able to create your own parametric PDKs for opsin circuit and Opto Designer as well. In this case, it takes a little bit while to calculate S matrix, or already calculate today. We can use the S matrix database to check the data we created here. So this is the S matrix data when the line imports into port 1, and we can see the phase and amplitude for all the ports here. So this is the S matrix for different port. Of course, we can launch the lines from different ports. You are able to see the S matrix data here. So we move to opsin circuit. We created a circuit here. And when you finish calculating the S matrix data, you will get a DTA file. So we use the user library organizer, choose the DTA file, and put it into our work group dictionary. And then you are able to use this custom PDK under your work group dictionary. So I already do that. Okay, so in this case, I need two outer coupler, two inner coupler in this case, and I'm gonna rotate this for 180 degree, and I want to connect them accordingly. And remember, once again, when we are calculating the S matrix, I don't want any actual waveguide between these components. So in this case, I used something that we called hard connection. So in the previous demonstration, the connection is the solid line, stands for we are going to do auto routing for this connection. But in this case, I don't want to do auto routing in this connection. So I convert this connection from soft connection to hard connection. So I use hard connection to connect them but I still need a soft connection to connect my port with the demo fab PDK grating coupler. So I convert this link from hard to soft. So in this case, Opto Designer only run auto routing for soft connection, which is the solid line, and it will keep the same for the hard connection, which is the dot line in this circuit. But before we convert this model to Opto Designer, we need to save this model and we want to check the performance, the resonance. So we use AppSync circuit. We load the compound model, load this model here, and there are 4 ports. You can look inside to check this is exactly what we just created for this case. So we can for 4 ports of this model.
Oh, hi Tung, your voice is breaking actually. I think he okay.
Yeah, sorry, it's getting weird for my internet. So I'm gonna continue here.
PDK, and then you can see the shift of the spectrum here. So now I'm very satisfied with this model. I save this model and then I open Opto Designer to check the model. So again, the script is generated automatically. I click update to check the layout to see what's going on in layout point of view. So here, basically, if you can see here, the custom PDK was loaded successfully, and the connection between them are perfectly connect with each other because we use a hard connection. We didn't add any actual connection between them, so they were connecting like this way. And the other part, we use a soft connection for the port with demo fab grading coupler. So we Auto Designer run the auto routing for this connection. And for the grading coupler one here, I don't like it to like this way, so I go to the code to change the orientation from 180 to 0 and click update to generate a new layout. So the interface between Opsin circuit and Opto Designer is the way for you to generate the layout easily and directly. And of course, you are able to change the layout in Opto Designer, or especially if you like to put it into your die template and send it to Fabrication, you can define the layout in Opto Designer. Okay, so make a little conclusion that in this demonstrations, we create custom PDKs by ourselves, create the layout tools, export the asymmetric data in Opsin circuit and Opto Designer. So in Opsin circuit, we combine these components together as a small little circuit, check the resonance, and export the circuit file to Opto Designer. So we're gonna move to another interface, that is the interface between Opsin circuit and Opto Designer and IC validator. So layout versus schematic is very important for PDA, especially when you are getting more and more complex circuit. So imagine you have a photonic circuit with thousands of components in this circuit. It's not even possible for you to check the connection, check the component name, and check the layout one by one by yourself manually. So in that time, IC validator can be very helpful for you to check the layout versus schematic. So in the case, Opto Designer enables black box flow by means of automatic mark layers. It will generate a GDS file with the spatial post-processing. And Opsin the spice net list from circuit model. So IC validators compares the list of connected components to schematic that is produced by Opsin circuit and the GDS file generated from Opto Designer. So in the flow, you can see here, in the original GDS file, information is present for all components, but however, LVS only wants to see the functional component. So just like a connection waveguides in GDS files, LVS doesn't check it. So in the case, we generate the GDS file from Opto Designers, and we use the script in Opto Designer to add the annotations on the GDS file. So IC validators check the spice netlist from Opsin circuit and the GDS file with annotations directly generated from Opto Designer. So in the case, we need to do the post-process for the GDS file, and we do these two flows separately, so we are able to check whether is there anything wrong in the GDS file, especially when we are doing some connections or routings, or we add some elements in the GDS files. So in the case, we can check whether we did anything wrong or not. So we are going to show you some examples in our demonstrations. Okay, so now we understand that the whole design flow for layout versus schematic in IC validator. So in this demonstration, I'm going to use the example file that we just created for our previous demonstrations, which is the IRE model with custom PDK. So we have 4 components connected with each other. And we have 4 DemoFab PDK, which are grading couplers connected with our components respectively with our auto routing features. And we are going to generate the spice netlist from Opsin circuit and generate the GDS file from Opto Designer. And we're gonna use the Opto Designer to do the post-process on the GDS file and generate a run set file. And then we are gonna use the IC validator to run the run set file to check the GDS file and the spice netlist. So our first step is to check the circuit model in Opsin circuit. So in this case, we need to make sure this model is exactly what we are going to design. And we can check the connection between different components because we use the auto route feature to generate this connection. So we now check we have auto routing building block in this connection. We can export the PDK spice file to our target folders. And I'm going to export like this one. So I save these models here and override it because I already previous one exported. So this is our first step. The second step here is go to Apto Designers and run the model, the Momo file, and generate the GDS file directly. So I didn't change anything. So I expect the LVS result will be passed because I didn't change anything, any connection. So for the GDS file. So this is the GDS file we just created. And now I'm going to run our post process. And in this post process script, we add some annotations on the GDS file and we create a run set file what we call output custom PDK. So now we have different files. We have a GDS file, and we have an output custom PDK file, and we have a spice file. So I just copy the new spice file into this folder because this is the folder that I'm going to work with IC Validator. So I open IC Validator, but before I do that, normally I will use the IC Workbench to check the GDS file, which is the one I used or not, because sometimes we load a lot of GDS file. Okay, so this one is the one we are going to use. So as we expect, the result is passed. So there's no arrows in this case. So we don't have arrow. So we have so many, all of our components are matched with each other. So that is what we expect. However, if you are doing layout and something wrong in your layouts, for example, if you accidentally add something in your layout. So in this case, I manually add tunable filters in demo fab PDKs, but this tunable filter is not shown in upstream circuit. So just like this one, so we do have a tunable filters, and I didn't notice it yet. So I start to generate a GDS file. So now in our spice netlist, we don't have these tunable filters, but in our GDS file, we do have this tunable filter. So we're gonna check here. We're gonna check the GDS file to check whether we have the one. Yep. So now we do have this actual tunable filter. So we go to Apto Designer to run our post process script. So in this case, it will read the GDS file that is with actual tunable filters. So we go to IC Validator, but again, I used to go to Workbench to check the GDS file. So in this case, you can see here the actual tunable filters now is shown in this GDS file. And I go to IC Validators, execute the same run set file because I didn't change the name of it. So I will check the new GDS file with the origin spice netlist because we didn't add actual filters in upstream circuit. So the spice file is the same as the previous one. So now we got a result is fail. So we can check the arrow. When we check the arrow here, we have something here. We have a lot of matched component, but we do have a layout unmatched. And the name here is the demo fab tunable filter, which is the one we just add in our GDS file. So in this case, IC validator do find the arrow and the point of where's the arrow from. So in summary, in this demonstration, IC validators help us to check layout versus schematic very efficiently. And when your circuit getting more complicated, this step is very essential to your design flow. So as I mentioned before, considering the co-simulation with EIC and PIC is important, especially when you have a complex chip with devices like laser drivers or electrical signal generators. For this case, Synopsys provides interface between HSPICE and opsin circuit, which enables users to integrate EICs and PICs in circuit-level simulations. Besides, users are able to import data by touchstone measurement of electrical network in opsin circuit, which is a common practice in the industry to measure performance of RF signal. So by the end of this interface, I believe interface with EIC and CIC will enable our users to have more complicated and more complete simulation platform for PIC chips. So let's look at how it works. The SPICE interface block converts the opsin input signal into voltage and current controlled source, and this electrical signal will be passed into SPICE model, calling it SPICE for simulation based on the SPICE file, which is loaded in this block. So once HSPICE finishes simulations, electrical signal will be outputted into opsin circuit again for the rest of simulation in circuit level. So the function of this block is to pass the signal to HSPICE and calculate the electrical simulation in HSPICE, then pass through the electrical signal back to opsin circuit for the rest of simulation again. Okay, so now we know that we are able to integrate electrical circuit to photonic circuit in opsin circuit. So I'm going to use this demonstration to show you how we use the SPICE interface block to run a co-simulation with opsin circuit and HSPICE. And this electrical circuit, which we are using here, is from our nonlinear laser models obtained by Opsin's best fit laser toolkit. So we had this electrical circuit, and we use HSPICE to create a SPICE file. We put a SPICE file in this block. So at first, we have generate logic signal and send into the electrical signal generators. So we connect it with an electrical filter. Now we send it to electrical driver. So we treat this one as a laser driver. So after this electrical circuit, it will be outputted to an electrical GAN model and send it to directed module laser directly. And then the electrical signal converted to optical signal. So the connection here becomes to red. And this optical signal will be sent into the optical normalizer to check the power, to normalize the power, and send into the photonic IC that we just created. That is our I ring. And then from the passport that we have, we are going to send the signal into the nonlinear fiber, and then we connect it with a receiver. We are going to check the signal profile and the eye diagram. So this is the demonstration I'm going to show you. So in this case, now we are able to run this case. So we're going to check that in this SPICE interface block, we use the laser.spice file here. So if you check one, this one is the circuit is generated by our best fit laser toolkit. and we use the electrical circuit here. So we're gonna use the HSpice to run this circuit, and after running this one, we use HSpice. After running this one, we're gonna get an electrical signal generated from HSpice. So now we are going to run it, and so we just simply connect all the models, and the iron here, we can look inside. That's just the one we created for previous demonstration. That is our PIC. So now we are going to link up the EIC with PIC in opposite circuit, and in the end, I used a nonlinear fiber to at the end of this PIC to calculate the signal after propagating through a piece of fiber and then connect it with the electrical receiver. We check the profile and eye diagram. So now I'm going to run this case. It takes a little bit while to run the simulation because now we are calling HSpice in the background to run the simulation in the electrical interface. And during that time, signal will be passed through our interface to HSpice first, and then after the calculation, electrical signal will be passed through opposite circuit again to perform the final simulations. Okay, so there we go. We finished our simulation. So we're gonna check the eye diagram for everywhere in this system. So at first, we're gonna check the eye diagram right after the HSpice model. So you see here, the signal was distorted by this electrical circuit. And we're gonna pass through this electrical signal to direct module lasers and pass through this PIC. So we can check this port, we check the eye diagram. So the signal is still keep, but the power is pretty low because the wavelength is not in the resonance wavelength. So in the end of this fiber, we pass through the fiber, we can still observe the eye diagram very clear. And have to convert the optical signal to electrical circuit signal. We are able to check the electrical signal, the profile here, and the eye diagram. So in this case, opposite circuit provide a very useful platform for the integration with EIC and PIC. And also, normally we use the this kind of PIC are going to be deployed in system. And it makes sense to design or optimize PIC from the system performance perspective. So in this case, we connect with the nonlinear fiber here. And actually, in this case, we use opsyn in this simulation. And because opsyn and opsyn circuit, they share the same GUI and the same user experience. So users doesn't need to learn a new tool to do system study. We can also integrate the circuit simulation with system simulations very perfectly in this case. So again, we use this case to try to demonstrate how to integrate the IC to PIC in the circuit point of view, and then we connect a nonlinear fiber to perform integration with PIC in circuit level and with the system level. Also, our users can do something more, like you can do DSP, or you can try to change the modulation format for your signal to get a optimized performance of your system. So after reducing those interfaces, we now are going to the final step, layout generation. So as I mentioned before, traditional IC design tool does not have the photonic elements. So for this case, Synopsys Opto Designer is an intrinsic tool for photonic integrated circuit. And our users will be benefited by using Opto Designer to save time and money. Just like Synopsys long-term partner Tower just said, we see directly when the design is met with the Opto Designer, very high quality, ready to fabricate it. So we go to the final demonstration for this webinar. And as we said, now this demonstration, I'm going to show you how to use Auto Designer to generate the final layout for our design. And now I'm going to use the same example that we just created from the custom PDK and demo fab PDK. So you guys very familiar with these examples. So in this case, I'm going to insert a single PIC into demo fab die template. So as you know, if you want to submit your design to fabrication, you need to follow the die template. You need to put your design into the die template that you can make sure that there's no anything wrong with for example, the size of your die or the connection of your die. And in this case, I'm going to put the design in the die template, and I'm going to run demo fab DRC in Auto Designer to check whether this design violates any rules or not, to make sure that I can fabricate these chips without any error. And in the final step, I'm going to export this error-free GDS file. So now I'm go to the Auto Designer here, and in this case, you see here, this is the model that we created from Opsin circuit. But in this case, I'm going to use this model in our die template. So at first, I'm going to create a die template with the package for the demo fab. So I insert this code, and Auto Designer will run the code for demo fab die template. So in this case, this is the default one. So when we check the layout here, so we can see the die template in this case. And in this case, I'm going to use the SOI technology. So I modify the code accordingly. So this is the chip, and I'm going to use SOI, so I don't need the Indian falsified technology or PDK. So in the die template, you are able to find a place to put your designs. For example, I put my design here. So this is the original one. I'm gonna delete it and go to the previous one. So in this case, I'm going to copy the code, part of code here, and copy it to this one, to this case. So now I'm just copy the code to the design play, and I can check the update in this case. So in this case, it's very easy that I put my design from the previous file to the die template. Of course, you can use it and you can save it as a SPD file and load this as SPD file in the die template in another way. But that is the demonstration for you to know how to put your design into the die template. So that is the way we do to migrate our design from the GDS file, from the Opsin circuit to a Momo file. Then we put it into a die template. So now, because I'm putting in the 200 and 200 coordinates, so it's shown here. So this is the model that I just created, and I put it in the die template. Of course, some die template they provide the port, for example, like gradient coupler and edge coupler. So in this case, you are able to use our connection features to connect your model with this port. So there would be another features that you can use. If you want to put more, if you want to prove something more, you can use the for loop to put more models in this case. For example, if I want to create a 5 model, I simply use the for loop in this case. And I change the coordinate for each models. So now, but I don't need to use the name for this case. So now I'm running the for loop. So I will create 4 models in this case. So normally people can test different kind of designs in Opto Designer. So in this case, you can set parameters in your unit model, and you can simply use a for loop to create models in your die template. Of course, the auto routing features was continue to perform in this case. So we still need to spend a little bit effort to route the next here. So that provide us a little bit of flexibility that we are not just import a fixed GDS, we are import script code. So in this case, now we are import four different, actually it's the same, they are the same, exactly the same layouts in the die template. So assume we are very satisfied with this case, you can directly click DRC. So when you click DRC, Opto Designer will check the design rule based on the foundries that you specify in this script, and we were gonna check whether any place for this design will violate the design route for this foundry or not. So it takes a little bit while to check the DRC because we are checking the different numbers of the design rules for this foundry, including the routing part. So that is why we spend some time here. So this step is very essential that the users need to check the design rule before exporting the GDS file. So I'm gonna make sure that we don't have any issues about this design, then I can export it as the GDS file. So now we are able to see here, there are no DRC error or warning. So you see here, we didn't violate any rules in demo fab. So now this design is an error-free. So we're gonna use the start to export the GDS file in this case. So normally our users are required to perform our DRC before submitting to manufacturers, and Opto Designer provides these very useful features for our users to check the design rules directly in layout tools. So if you find something violating your maybe the foundry rules like the sharp angle rules or the distance between two waveguides, they are too close with each others, so you can directly modify it in Opto Designers and check it again. So you don't need to switch to back to another software to check the design rules in this case. So it would be very helpful for our users to check the final and verify your final designs, whether it works or not. So here, now I already export my GDS file in the, I think in the C folders. So I'm going to talk to the C folders, and not this one, this is C folders. So we're going to check, now we're gonna check the GDS file. So we do have the GDS file here, so you can check different layers. For example, the 01 stands for the trench layer, so we can check whether there's a matrix good or not. So in this case, the GDS file performs very well, so including the custom PDK here. So in this case, we use the custom PDK and DemoFab PDKs, and we can generate the GDS file directly and correctly. So we also use the DRC functions in Opto Designer to check the design rules for this case. So far, this is the demonstration for you guys to know how to insert several single PICs into a DemoFab die template and run DRC, then export an error-free GDS file. So after this demonstration, I would like to make a conclusion. In summary, Synopsys focuses on a completed design flow enabling our users work from ideal to fabrications. And this demonstration and these webinars are starting from the concept of EDAs, and now we are working make it work as EPDA. And finally, Synopsys provide a PIC design soup along with our expertise, and then we want to make PIC design as an automatic flow in the near future. So this is our design suite from concept, ideal to fabrication. Thank you for your attention.
Yep, so this is the first part. This is the first part for my presentation, and I got few Q&A, so I would like to answer Q&A first.
So thank you, Tung. So for first completing first part, so we have couple of Q&A. So first question is the basically what type of meshing used in ring regenerator simulation example file?
Yep, so that the first question is for a re-representer. So we use the full wave FDTD. So the meshing I use non-uniform mesh in the FDTD simulation.
Okay. Second is what kind of source is used for the simulation?
Yep. So I believe that simulation in the re-representer is used the SLAM mode, the propagation mode for the waveguide. So that means that the light is just like propagated in the waveguide and connected to this device. So the source is propagation mode.
Okay. So third question we have, which algorithm is used for the simulations?
Yep. So if you're talking about the custom devices that I use full wave FDTD, finite difference time domain.
Okay. So next is it required heavy computer system to run all long simulations in Synopsys?
Yeah, it depends on what kind of simulation. If you like to, for example, if you like to run simulation for such a big circuit, I would say that is impossible. So we need to divide it into different pieces of devices. But if you like, you can use a computer to run simulation for the small piece of devices. That is possible. So it depends on what kind of scope of a simulation that you would like to perform in your computer.
Okay. So next is does Synopsys have facilities to optimize fiber coupling to waveguide to check how much percentage of power transfer and loss?
Yes, for the fiber coupling, if you are talking about grading coupler or vertical coupler, full wave FDTD is a very suitable tool for 3D simulation. And if you are talking about edge coupler, I believe BIMPRA BPM would be a very good solutions for you to do that. So you can contact us for this kind of algorithm, and we can suggest what kind of tools that you can use.
Okay, thank you. I think we have all these questions. Now you can go to your next part of the presentation.
Thank you, appreciate. So I would like to share my another script. So we are just talking about the simulation flow, and I would like to try to extend our topic for based on that one. So let me share my another screen here. Yep. All right. So, and let me do that here. All right. So I think that this is a very special topic that we can talk and we can discuss in this seminar. We would like to introduce the co-simulation of integrated photonic devices using Centauro's Tcat and R software. So this is a very special one. And normally we know that just in the previous discussion that we are able to use the RSoft device tool, but then we figure out that there might be something that we can do more. For example, if you would like to run the simulation with more complicated doping profile, and in that case, I believe that you might need to use some professional tools for the device part or the process part. So that's the reason why we would like to introduce this flow today. So the flow, the example that I'm gonna show you today, that we will have a few examples that we're gonna show here. So the first part is I would like to talk about the interface between our software and CentOS Tcat, and I will have two examples in this case. And then I would have some overview for the two. So the first one is why we need to do such a simulation. So normally we know that there are three kind of devices that we call active devices. There are three kind of active devices we're gonna use in our design in our design of PIC. So the first one is laser source, that is light source. So laser source means you use electron to generate the photons. And so far, I didn't see any foundry who is able to integrate lasers into their silicon chip in a commercial way. I know that we have some academic researchers, professors in their lab, they are able to integrate light source into their chip, but I didn't see any foundry who can provide this kind of service in the public. So normally for the first one that people are able to do the research about that, but when you are talking about you want to use the multi-project wafer, I didn't see any foundry provide this kind of service, but we hope in the near future, this will be a very possible solutions because that is the very important part for the PIC design here. And the second one is the photo detector, or we call photodiode. So photodiode is just transfer photons into electrons. So in this case, that there are several foundries they are able to provide a service. That is, you are able to integrate your PD in your chip. And the final one, modulators, is the most important one for photonic integrated circuit because that means you are able to control your optical signal by electrical signal. And in this case, that we would like to use the photodiodes and the modulators as the example to show you that this integration between our soft devices and for CentOS Tcat. So what is Tcat actually? So Tcat stands for Technology CAD. Technology CAD. So Technology CAD, that means you used some physical model, and those physical models are based off very essential equations or models in semiconductor process and device simulation. For example, you are able to simulate the dopant profile. You are able to simulate the dopant profile with the condition of your processes. So for example, you are able to use the temperature, the power for the input, and you are able to get a dopant profile. So that is very powerful for the simulation of a dopant profile. And of course, you know that what I'm talking about is about process. So our software is not able to do that, but Synopsys do provide CentOS Tcat for this kind of simulation. And that is the professional area for CentOS Tcat. It's more about the material area here. And then we can do some device simulation. When you apply the voltage, that you will know that what is the current and what is the dopant carrier distribution at a specific voltage here. So this kind of simulation, which is not exactly related to optical and photonics, but they are very important if you want to do this kind of active devices. So that's why we would like to use the CentOS Tcat for this two part of simulation. And our interface is we are able to use our self-device tool to integrate with CentOS Tcat, and we integrate our tools in CentOS Tcat Workbench. So now we would like to link them up together to confine a EPDA tool set together. So that is, users are able to have more complete and comprehensive tool set for this kind of active device simulation. So let's check the first one, that for CentOS tools, that CentOS Tcat uses CentOS Workbench and a lot of different modules. For example, the CentOS Structure Editor, CentOS Device Simulators, and CentOS Feature, CentOS Process. And we just integrate our soft devices tools into CentOS Workbench. So you see here in the middle of this Workbench, it's just like that there's a function, there's a tool, there's a module called RSoft, and it is integrated in the workbench. So that will be very powerful and helpful for users, because you don't need to worry about, for example, you don't need to redraw your geometry. You don't need to recreate your model, redefine your material. What you need to do is just input the file and implement the RSoft in your CentOS workbench. And the working flow is always controlled by the simulation script here. So it will be very easy if you are familiar with CentOS Tcat. And actually, the geometry, what we need to load in RSoft is exactly from CentOS Tcat. So that is, you don't need to recreate a structure, as I mentioned. So we just read the structure, read the material, and we run the simulation in RSoft device tool. Then we can put our simulation result back to CentOS Tcat for device simulation. So that is another thing that we can try. And this interface is a bidirectional data transfer. So we can read the data from the CentOS Tcat, and we can also output the data to CentOS Tcat for device simulation. We will have another example file today for the detector to show you how we're gonna do that. So the advantage for combining RSoft and CentOS Tcat, we can see here that we just combine two market-leading simulation software, and all the passive RSoft simulators can be used. So it's not only for full-wave FDTD. We can integrate with SpinPrep BPM. And the RSoft tools are integrated into CentOS Workbench directly. So it's the complete integration flow. You don't need to change your computer. You don't need to relaunch another program. You just need to use the CentOS Workbench as you did before. So another thing is you don't need to draw the geometry. And there's no messy file format conversion. We just read the send file. So you don't need to worry about the file format. You just need to use the send file for all the simulation. So let's see the first example, a 3D free carrier silicon integrated modulators. So in this modulator, this is a longitudinal PN junction distributed modulators. You have the PN junction along the duration of the waveguide, and because of the short distance of each PN junction, the response is faster, and the structure will vary the structure will vary in all 3D structures. So that is that we need a 3D solver. So that's why we use the CentOS Tcat and RSoft SpinPrep BPM. So in this case, that we would like to use the tools for this kind of simulation. So at first, we use SDE to create a structure. We use STE to create a structure and define a material. And then we use S-device to calculate the carrier distribution based on different applied voltage. For example, if you have 0 voltage, you will have a distribution of the carrier. And if you increase your biasing voltage, that you will, for example, to the -3 volt, that you will have another distribution of carrier. So that's why we need to do that, because we would like to check the phase delay for when you apply different number of the voltage here. So for the first one, we draw the structure in SDE. We create this kind of geometry, and then we export a boundary TDR file. We export the boundary TDR file, and we use the boundary TDR file as the interface from CentOS Workbench to RSoft. So this is the interface that is the file format in the standard file format in CentOS Tcat. We just read it. And then we run simulation. We apply the voltage. We use S-device to run the simulation. We know the electron density distribution, hole density distribution. And then we are able to convert the distribution of carrier into the perturbation of refractive index. When we are running photonic simulation, the most important factor is refractive index. So every single possible issues which can contribute to the change of the refractive index could be taken into the simulation in this case. So for this case, that the density of electron, the density of hole will change the refractive index. So that's why we need to convert the distribution into refractive index. Then we used our sub-data, load the structure, load the index. For example, there are two curves here. And for the green one is the V equals to 0. And the red line here is the V equals to -3. So you see there's a tiny difference between when you apply a different vault here. And then we run a simulation, we calculate the mode, we calculate the input fiber mode, waveguide mode, we run a beam propagation method, and we can get a shifter like, for example, we can get a phase shifter, the phase shift along with how many volts they're gonna apply in your structure. For example, if you apply 0 volt, the initial phase is like 12 degree. And if you apply -3 volt in your structure, you have 0.15 degree phase change here. So this is the very quick video that we're gonna show here. So for example, this is a structure versus a structure created by SDE. So remember that if you use the mesh boundary TDR file, that you are able to get this kind of information. You are able to get your structure, your material, or the doping concentration. So that is the first status, the doping concentration. And then we run the simulation with S devices. We apply voltage. We apply the voltage on the BIOS and ground. And we have four files. The 3 stands for the voltage equals to -3 volts. So when we apply the -3 volt on this structure, you will see the density distribution. You will see the density distribution changed. And this is what we want, but we want to put it into our self-device tool. So once you have this kind of structure and this kind of distribution, we are able to convert that into a reflective index and run simulation. So in our self-device tool, that you just open the CAD, you open our self-CAD as a normal way, and you see here the structure is loaded automatically. You don't need to rebuild the structure. You just load the TDR file, and the material structure can be loaded automatically. So if you check the script, that every single step would be described in the script here. So that would be very straightforward. If you are doing something more complicated, you are able to use the script language to run the simulation here. So let's run the simulation, click run. And first we will calculate the index perturbation. We will calculate index perturbation and calculate the mode, run beam prop BPM simulation. So you see here, the simulation speed is very fast because we use beam prop BPM simulation. Of course, you are able to use the full-wave FDTD, but it might take a while. For this kind of structure, a phase shifter, I believe that beam prop BPM is a suitable and good tool for you to estimate the phase changes when you apply the different voltage here. So now we just propagate a 3 micrometers waveguide and phase shifter, and you will see the phase change later. So there are two curves. The blue one stands for the phase, but it's repeated, so it looks like a little bit weird. So when we are finished our simulation, then we will get a plot. You are able to get a plot directly. You are able to get a plot in our self-data browser, and you will see there we generated this kind of plot. The phase changes when you change the BIOS voltage here. So that is the integration example for the first one, free carrier silicon modulators. So we know that now we just passed the structure and parsed the information from Centaur Tcat to our soft. And we mentioned that this kind of interface is a bidirectional interface. So we have another example we call 3D silicon Germanium photodetector. In this example, this is a full 3D silicon germanium photodetector, and it's coming from IBM's IDEO here. And we know that the functionality for photodetector is to convert photon into electron. So first, we need to run optical simulation, calculate the absorption, and the device simulation will turn the absorption into photocurrent. So in this structure, the working flow is like we create a structure first and run optical simulation either by beam prop BPM or full-wave FDTD. So once it finish that, we will get the absorption profile, the absorption distribution in this simulation. And then as devices will read the absorption and apply the different voltage on it, that you will get the photocurrent in this case. So this is a structure. We use SDE to create structure. If you are familiar with Parcel, you can also use Parcel as a simulator to create your structure with the different doping profile. And of course, in this case, that some of the material are used from the library. So if you use the material directly, that you can directly, the material will be directly imported into our Tcat. You don't need to worry about that. So in that case, that we need to run a simulation in our software. So we also use the script to describe the step. First, we calculate the mode, and we calculate the propagation. And finally, we convert the output file as the TDR file, which will be read in S device. So in this case, we use Tcat to read the material structure. We use full wave FDTD. We use spinprop BPM, and we want to do the comparison. And we use WinPlot or data browser to do the visualization of this case. And in this case, that in simulation, first we calculate the input mode, the waveguide mode, and we run the sim propagation for this optical diode for the diode. And you will get a distribution. Of course, it's a decayed distribution because the light was absorbed by the material by germanium, and you will get a distribution. And we want to record this optical generation as the absorption field in the RSOF. Sorry, yep. And then we run a simulation in S devices. We are able to get the amount of photocurrent when you change the applied voltage here. And when we also do the comparison, when you do the beam prime and full wave, you see here the difference is very tiny. Difference is less than 5%, but the speed is a lot. It's like beam prop BPM is about 50 times faster than full wave in this application. So you can use the more efficient tools for your simulation based on the structure and geometry. So if your structure and application is suitable for beamprop BPM, I would suggest you to use beamprop BPM to get a faster and efficient simulation with very close result comparing to full wave FDTD. So there's a demonstration video. At first, that we create a structure. We create a structure in SDE. Once again, it's always possible that you use Parcel to create your structure. So this is the structure. This is the for the detector structure. And these files models are in our example library. So if you're interested in this example, that you can just let us know. We can share this example without any issues. And then we run the simulation. But first we load the structure directly in our Tcat layout. We load the structure in our Tcat layout. So you see here the structure are automatically loaded. You don't need to worry about that one. You just need to open the tool and to read it to visualize the structure. And of course, we use a script to control the step. We use the script to control all the steps in this case. So you can do something more complicated or fancy here. So when run simulation, you can run simulation. You can run a lot of different simulation together. And yeah, so because full wave simulation take a lot of time. So in this case, the full wave simulation is speed up for 50 times. So now it's a speed up. So in the real case, that you might spend like several tens of minutes to finish the simulation in this case. So far that the simulation, the time here is speeded up. And this is full wave FDTD simulation. You are able to see the structure simulation in time domain. And in this case, that we run several simulations at one time. And then the next step is we can visualize the different power or the different, not here, the different watts. So you see here, this is the absorption distribution for the first one, for the bottom, that you will have the stronger absorption. That is because this is the first part that the light propagated. So for that case here. And then you can see that after the using the absorption, that you are able to get the IV curve for this case. And this time we use BIMPROP BPM. And please note that in this case, the video here is not speed up. It's just the real time. So you will see here the propagation. You will have some noise because there's a lot of metals on it. But once the simulation get converged, that you will get a very close simulation result in your script here. So that's it. We finished the simulation. So you can see the difference between two different modules, and the difference is very huge. For this case, it's like 50 times faster. So that case is very helpful for you to evaluate your structure in the very beginning. But of course, we always suggest you do the final validation by forward BIMPROP in your final stage of your design. So you see here, this is the IV curve for the result in BIMPROP. So if you do the comparison, you will just get what I show you in the slides. You will just get what I show you in the slides, that they are very close. The difference between BIMPROP BPM and forward FTTD is less than 5%. So that is a good way for us to evaluate this structure with a suitable tool. So let's move to the conclusion for this section. So the first one is the RSF component tool now actually is fully integrated in CentOS Workbench for a long time. I think that we started this project in 2018. So this tool, a lot of different customers already heavily used this integration in CentOS Workbench. So we got a very good feedback. And by the end of the bidirectional RSF/Tcat interface, that would be very helpful because they use the same file format. You don't need to worry about the geometry, the material, or even the mesh. If you are talking about the numerical methodology, you don't need to worry about the mesh. And also tool can read the data and output the data. So there's no any format conversion in this case. And of course, that we also include the mode solving and propagation analysis. So it's very suitable for photonic integrated circuit, especially for the active devices like photonic detector and modulators. So this is the first section. I would like to, and thank you for your attention. I'm very happy to answer all your Q&A here.
I have, I think, two questions.
Yep.
So first one is can we use all optical designing and solving tools like RSoft in the CentOS workbench?
Yep. So actually, this integration is for our soft device tool. So all the passive RSoft device tool can be integrated in CentOS Workbench. But of course, it always depends on what your application. For example, if you are doing a periodic structure, you can use full wave FTTD or different mode RCWA. But if you are talking about the modulators, like what I show you today, you can use the BIMPROP BPM and full wave FTTD. In this time, our different mode RCWA might not be suitable, but it's always integrated in this workbench.
Okay, so other question is how to calculate mode area and volume, confinement factor, Parcel factor, and Q factor of microcavity.
Yep, I believe this is another question, and I'm very happy to get this question here. So, if you're talking about how to do that in the integration of CentOS Tcat, I would say that that is always possible because we use a script. But if you are asked this question by the no more basic usage of this one, and I would suggest you to contact us after this meeting. You will have my contact information or the Mr. Provin's contact information that we can solve this problem, or we can help you to teach you how to answer the question after the meeting. Thank you.
Okay, so next one more question we have. Can we import unknown material? Can we import unknown material if that material available in Synopsys library is not available? I think how to import?
Yeah, you're right. Maybe it's unavailable. So if the material is available, then it will import directly. If the material is unavailable, that you can always use the manual work to import it. So in our sub tool, that you just define the new material. You can define a new material with the same name. the name is very important. If you already, for example, if you use the material code blue filters in CentOS Workbench, then in RSF device, you also need to code a structure, code a material as blue filters and use the same name, and you can always import the data here. If you would like to know more details, steps here that we can discuss later after the meeting, and you can contact us for more instruction here.
Okay, so I think that's all for questions for this session. So you can go to your next session.
Yep, thank you. So let's move to the final section, and I would like to thank you for joining this training for almost 2 hours. It's a long time, but I hope that you guys and I also learn a lot of things for this case. So the final section for Synopsis section is that I would like to introduce another new unified photonic IC platform. So in the beginning of this section, that I introduced Photonic PIC design suite. So that is a very helpful and a very powerful design suite for the design. But realize that we know that for the photonic design that we need a unified platform to design your structure instead of change your structure between upstream circuit and Apto designer. So this is the first, this is the new platform that I would like to introduce to you. If you are familiar with upstream circuit and Apto designer, let's say, okay, we are still supporting them. But if you would like to find a new and unified platform for photonic integrated circuit design, I believe that the following instruction for the Apto compiler is very helpful for you. So I just skip here. So in this case, that we know that if the evaluation of software is getting more mature. So in the beginning, if you would like to do the photonic design of an integrated circuit design, you need to be an expert at photonic integrated circuit because you don't know how to connect the waveguide. You don't know if you don't know the phase, if you don't know the resonance, that you are not able to do the photonic circuit. But we know that in order to make the photonic integrated circuit more available to a lot of different researchers that can focus on their real design, for example, the signal, that the simulation tool should be the key issues for them. So our goal for the simulation tool is we would like to that the engineer who might not be an expert for photonic, but maybe he is an expert for signal process. She is an expert for the data structure. So for this kind of structure that we would like to them use our tools as easy as possible. So that's why we need to introduce this platform, unified platform in the design of photonic integrated circuit. So that's why we call that we have the Apto compiler. We have Apto compiler. Apto compiler is the brand new uniform platform that we just released in the last September. That is 1 year ago. We released Apto compiler to the public. So we just follow the same procedure. We have circuit simulation, we have Opsin Elite, and we have devices simulator. We have our device compilers and our Tcat that we just introduced. So the basic flow is very similar to the previous one for the first section, PIC design suite, but we make them more unified. So in Apto compiler, that you will have interactive design environment. That is, you don't need to write a script. If you're doing some easy design, you can use your mouse, you can draw, and you can draw your structure, you can do something schematic. And of course, it's integrated with the professional tool like Opsin Elite, IC validators, Photonic device compiler, and CentOS Tcat is all integrated here. So I would like to show you here. The basic concept is you have an idea. For example, I have an idea about my chip design. So just assume that, for example, I'm not very familiar with photonic, but I have a very great idea about the circuit. When I have the very good idea about a circuit that I can use the concept of my idea, I can draw the schematic in Apto compiler, and I can turn that into layout directly. I don't need to move to another software. I can just turn the schematic into layout. So in this case, that we will have the name for this function we call schematic driven layout. you can use the schematic, you can use the connection in a schematic and directly put it into layout. You don't need to recreate a lot of effort. And we also do the simulation, we also do the LVS, and we also run DRC and final tap out. So you see here, the basic workflow is very similar to the first section that we just mentioned, but we just unify them together. You don't need to switch a tool, you just step in the same tools that you can finish all the job here. So for example, the first one is that a opto compiler. Yeah, but I just would like to make sure that I'm sharing the same. Yeah, I believe. Okay, I'm sharing the correct screen because I'm just curious whether I'm sharing the correct screen here. Yeah. All right, so in AutoCompiler now, schematic, you're able to check the schematic. You are able to view the schematic here. And in the schematic, the connection between photonic devices with photonic wire or electrical devices by electrical wire is very clear and very easy to understand. So the components can be from photonic PDK and electrical PDK in this case. So everything now you can do that in schematic editor. You can do something very similar when you do the in option circuit. So you just draw the model, devices from foundry PDK and put it into your models and connect them in the correct order based on your design. Then you are able to do something very fancy here. And in the layout part, so now the layout, you can use your mouse to control the layout. So remember for the first section that we use the script, to control we use a script in Opto Designer to draw the layout, but in this case that you are able to use your mouse to control and to draw the layout. So that would be very helpful for if you are very new to the scripting, you don't know how to write a script, you can always use the interactive interface in the Opto compiler here. So I would like to have the video here to show you that one. So in the layout editors that you are able to align the structure. So you see the fly line between these two devices. That is the relationship in the schematic. So in the schematic, you define these two components, they are connected together. So they are connected together and it's automatically connected. So if you put these two semicircle closer, that it will be connected. And if you change the width, for example, I change the width here and put it here, you will get a rejection. You'll get a rejection because the widths are mismatched. So it's auto detection that if you put something different, that this kind of rejection will help you to check whether you are doing something right. If you are doing something wrong, then we will get this kind of warning message. So this kind of alignment is very helpful for you to do this kind of thing. You don't need to manually calculate the coordinate. And in this case, the alignment will be helpful for you to do that. And the second one is if you have a lot of tools to do that, we also provide a group alignment. We also have the group alignment. You can have a lot of you can align all the devices together. So for example, for the first one, I rotate the grading coupler for a specific angle, and I select all the rest devices after the grading coupler, and I do the alignment, align the first devices. So you see here, all the devices are rotated because they just realigned to the first one. So you don't need to align the structure of the device one by one. You can do something like that. You can align a group of the device simultaneously. So that would be very helpful for if you have some modification for the first structure. All right, so another thing is for the connectors, we also provide the connectors for our users. So you are able to connect your structure automatically. You don't need to calculate the actual position and how many bands, how many straight waveguide, 90-degree bending you're gonna use. You can use the connector directly, and all the component will be back annotated from layout to schematic. So remember our first demonstration in the first session today, I used the band switch and I used the auto routing. When I use the auto routing, I need to go back to schematic to rerun a simulation because those kind of additional waveguides will contribute the changes or the effect or in a simulation. So the back annotation is important, and it's also feasible in this case. So this is the case that we're gonna show you the connectors. So you see here we have the different devices. You have different devices here, and we connected them together, and we use the connector. So now the connector will calculate the starting point and the ending point. So when you switch when you change the position of the first device, it will automatically connect them in a very fancy way. So you see here, there's no gap, and it will calculate in the system. You don't need to worry about that. And when you do the back annotation and go back to here, all the devices like band and straight waveguide will be back annotated from layout to schematic. So for example, if I change the position again, then you will run the new connectors, you will get a set of new data, then you can run simulation. So when you talk about simulation, OpSim is perfectly implemented in Opto compiler, and we modify the name as OpSim Elite because we want to separate the OpSim standalone and OpSim Elite. So in this case, the OpSim Elite is the solver. In Opto compiler, we use the OpSim as the solver in the background to run the simulation. So all the previous simulation that are able to be run in Opto compiler. So, and of course, the simulation that I introduced in the first section can be also do that in Opto compiler. So what you need to do is you have the schematic, and you can connect the OpSim models. You have the monitor, you have the laser source, so you can put an OpSim model, and you go to prime wave or SAEs in the Opto compiler. You can run the simulation. When you run simulation, OpSim will be the simulators in the background. OpSim is the simulator in the background. Then you are able to code the OpSim viewer in the SAE structure, and you will get a result here. So OpSim now is fully and completely integrated in Opto compiler. So that would be very helpful for you to run a simulation. And of course, for example, if you do the back annotation, you can use the OpSim as the simulators for action. So I think that this is a very quick introduction. So in the previous step, we also mentioned the custom PVDK device. That is always feasible. So we also provide the users, you are able to follow the same step, create your screen arch layout, run simulation, get the asymmetry, for your custom device. You can export your custom device into Opto compiler, and the layout, the asymmetries will be generated automatically. So all the you don't need to switch OpSim circuit to Opto Designer. Now they are all included in Opto compiler. That is the first unified platform for all the tools. So yeah, I guess I lost the connection. They just lost the connection. But this is my final slides that we are working with with a different foundry, for example, Tower Semiconductor and Glow Foundry to implement more easy use the PDK. So that is, you can use the photonic PDK like electrical PDK. You don't feel any difference. So that is our vision. We want our users to treat the photonic PDK as electrical PDK. So what is the difference between, and what is the reason why we need to do that is because we would like to enable a fast and accurate result in our platform. So by the feedback from our customers, our main users that, for example, Rockley, they just provide a very good feedback for us, very positive feedback that thought the Opto compiler help them to shorten the simulation time and the design time, and it's very efficient and very quick. And of course, the integration with everything like layout and schematic is very helpful for them. So I believe this is my final slides for the final section of the seminar today. And I would like to, if you are interested in this kind of devices or tools, you can feel free to reach out us, and I will provide the necessary information for you.
Okay, so thank you, Tung. I think we don't have any questions for this session. So thank you again for the wonderful talk. And I think we can end up the session. Kishore, if you want to share something, you can say.
Yeah,
Right.
Anuj, you can announce the next event.
Okay, sure. I will announce the next event. So, yeah, let me quickly share my screen. Okay. Okay, so yeah, I think my screen is visible. So, in the uh, continuation, we have the talk on the in this symposium. We have talk on ANSYS numerical for the PIC design on numerical platform by Mr. Ankush Sharma, who is application engineer. And a very good talk we have by Professor Chinupati Jagdish from the Australian National University, Canberra, on the topic of semiconductor nanostructures for optoelectronics and applications. So everyone will receive the email for the all uh, for both of these talks. This talk is on the, I think, 4th of September, and this is on the 5th of September on the Teachers' Day. So hope everyone will join, and with that I will end the session. Thank you, Tung, again for the wonderful talk. So yeah.
Thank you.
Thank you, Mr. Tung and Mr. Praveen Joshi for collaborating us in giving the wonderful talk at Photonic Student Chapter IIT Bombay. We're really thankful, and in futures we'll again collaborate with you for the more advanced talk. Thank you and have a good day.
Thank you. Have a nice evening.
Thank you, Kishore. Thank you, Kishore. Thank you, Dr. Anuj Bhatnagar.
Thank you, Chef.